Okay, so today we are very happy to have Giovanni Ferrer from Ohio State University. So he's 6-year graduate student at this university, working under the supervision of David Penneys. His research interests include higher category theory, functional analysis, and the interplay between these emerging from quantum symmetry, topological quantum field theory, and condensed matter physics. And today he will talk about higher Hilbert spaces and their operator algebras. Giovanni, please.
All right. Well, thank you so much for the introduction. First, I want to apologize for not making it to the last seminar. I got confused about the dates, but I'm very happy to be here today. I've gone through Quan Chen's talk, at least his slides. I know that he talked about a similar topic. So my goal today is just to revisit what he talked about, maybe give some of the easy details, and then maybe some of the broader overarching ideas. So first of all, is the text size okay? Like, can you read it? I know it's a bit small.
The abstract is a little bit small, but
it's very small. Okay. Well, it's a good thing I can zoom in. Okay. I'll keep that in mind. All right. Lots of topics. So let's see how we do. Okay. So this is, I guess, not just mine, but our research group's broader research program involving functional analysis, higher functional analysis, and higher Hilbert spaces and their operator algebras. So it's all centered around this staircase. There's a bunch of recent work related to this staircase, as well as maybe some older texts. I've included 4 here, but let me try to describe this for you. All right. So hopefully that is visible. Okay. So say that we care about Hilbert spaces, right? Well, if you have a Hilbert space H, maybe I'll do this with blue. You can try to study its symmetries, and what you end up studying is well, you look at operators that act on these Hilbert spaces, and when you look at the collection of all of them, we'll call this B of H. This forms an operator algebra, and here I'll be using operator algebra kind of agnostically. I might mean C star, W star, H star. But in general, these are just operator algebras that act on a Hilbert space. And the prototypical example of an operator algebra is the collection of all bounded operators on a Hilbert space. Now, of course, you can quickly generalize depending on your flavor of operator algebras and just consider any subalgebra A. Great. So what I want to convince you of is that if you take an operator algebra A and you form its category of representations, whatever I mean by representations, this will form something analogous to a Hilbert space. Okay. And so we'll touch on some key properties that make it analogous to a Hilbert space. But if you take me at face value that this is true, then you can start thinking about operators on a 2 Hilbert space. So you may think of something acting on a 2 Hilbert space, and then again the collection of all of these. Perhaps let me call this. Let me do it like this. A 2 Hilbert space is bigger than a Hilbert space. I'll be using a fancier font to talk about a higher Hilbert space. So this is a fancier H. And then as you consider all operators on this 2 Hilbert space, you obtain something akin to B of H 1 level down. Maybe I'll call it B of fancy H, which is your prototypical example of a 2 operator algebra. it will be a monoidal category. And then again, depending on what flavor of operator algebra you're interested in, it might be a C star tensor category, W star tensor category, or something with more structure. Great, and then you could consider subalgebras of this. For a two-operator algebra, I'll use a fancy A instead of a normal A to indicate that I've gone up a category level. And again, you can consider its representations, whatever I mean by that. And somehow this should be an even higher Hilbert space, which we call a 3 Hilbert space in our paper. And so again, you could continue up and up this staircase. There's a bunch of work done. So let's see. Where do I start? Well, okay. In this 3 Hilbert space paper, we go through this story concerning Hilbert spaces, 2 Hilbert spaces, and 3 Hilbert spaces. And this is only in the finite dimensional story. So I'll tell you why we care about the finite dimensional story. And I know that Quan had a slide at the end of his slides where he talked about infinite dimensional things. I don't know exactly what he said because I don't have access to that, but I'm sure he said something cool. So if you have any questions about that, please feel free to ask me. What else? There's this recent work. These 4 papers are all on from last year. There's this paper from Enriquez, Nivedita, and my advisor, where they developed 2 Hilbert spaces in the infinite dimensional case, or at least a good analog for what a 2 Hilbert space is. It's infinite dimensional. There's some other work. This is perhaps more foundational. There's this little preprint that I wrote, which concerns itself with, I guess, setting up the foundations for operator 3 algebras and 4 Hilbert spaces. This is particularly for these things called C star 3 categories. And then there's this even more general work. Me and 10 other wonderful human beings. I'm sure you can find this pretty easily on the internet. This is for Tegra N categories. And that's pretty much the first ingredient that you need if you wanted to talk about N Hilbert spaces in full generality. Let's see, I'm sure I'm forgetting lots of other things to cite here. What can I say? Perhaps I can say this. 2 Hilbert spaces were introduced by Baez, John Baez. This is in 97. What else? We're also writing a textbook. This is called UQSL. This is my advisor, Dave Penneys. Who else here? Kyle Kawagoe and myself. And we essentially talk about this whole picture with all the details. So you can find that online. At the moment, I guess we only have the story up to around here. Hilbert spaces, operator algebras into Hilbert spaces, and we'll keep adding more online. So let me tell you, what can you Google to find this? I think if you just look up unitary quantum symmetries, light, textbook. You can find, I think we have 5 chapters up right now. So if you're interested in this stuff, you can take a look at that. But anyways, that's enough for that. Now I'll try to describe some actual math. Okay, so why do I care about this stuff? Well, there's three motivations. One of them is coming from quantum symmetries. I guess this is the quantum symmetries seminar. So as you know, the classical symmetries of a set are captured by a group. But then if you care about quantum systems, you might want to consider symmetries on a Hilbert space or a two Hilbert space or an operator algebra. And so for an operator algebra, it's quantum symmetries are captured by a tensor functor from a monoidal category of whichever flavor you like into the monoidal category of bimodules for that algebra. And one important example that comes from subfactor theory is the standard invariant, which a lot of us know and love. And that's generated by the action of one particular bimodule. I won't bother describing it. Okay. The second motivation is from topological order. And this is in particular the particular reason why we cared about the finite dimensional story, aside from the fact that everything is way easier in finite dimensions. If you're thinking about lattice models and you're thinking of like a finite lattice, and then the states at a particular vertex is a finite dimensional Hilbert space, then everything is nice and finite dimensional. So that's one particular motivation. And another one is coming from topological quantum field theory. In particular, if you're thinking about unitary TQFTs, higher Hilbert spaces are expected to serve, like they should be the appropriate receptacles for fully extended unitary TQFTs. What else can I say about this? Well, I guess it depends on your flavor of TQFT. But if everything is nice and dualizable, then whatever you're sending things to should be finite dimensional in some appropriate sense. So this is a good start for this program, I guess, is what I'm trying to say. Okay, I didn't read any of what I had on the slide, but okay. So let me tell you something about Hilbert spaces. This slide is going to seem quite silly because all these facts are trivial, but I want to create an analogy with what's going on for two Hilbert spaces and three Hilbert spaces. So for Hilbert spaces, one, these are complete with respect to Cauchy sequences. You have bases, right? So every Hilbert space admits an orthonormal basis. And moreover, the space of these orthonormal bases is contractible. You can think of it as E of the unitary group of H, whatever that means. But essentially, it's okay. It's not evil to choose a basis because their space is the space of such O and B's is contractible. So you could contrast that to, for example, choosing a inner product on a vector space. Right? This is choice. This is more structure. But somehow choosing an orthonormal basis isn't really more structure because this space is contractible. Just kind of curious. Okay. And finally, Hilbert spaces admit evaluations of oriented zero spheres. So what do I mean by that? Well, a zero sphere is kind of dumb, but a zero sphere is just 2 points. So what I'm saying is if you pick 2 points in your Hilbert space, say, let me call my Hilbert space H. This is just a choice of a pair of points. I'll call it C and eta. And then your inner product allows you to evaluate this zero sphere in order to yield a number. Okay. Now, the fact that it's Hermitian tells you something about being able to evaluate oriented zero spheres in an oriented one sphere. I'm not going to get too much into that, but essentially you can flip the 2 points around at a cost of a conjugation. Okay. There's lots of things you can do with Hilbert spaces. For example, you've got vectors, you've got scalars. You can act with a scalar on a vector. What else? Let me use one of these. Okay. Right. So you can scale any vector with a scalar, and that gives you another vector. You can also add them. You've got this complex valued inner product. And then, of course, you've got the dual Hilbert space, which is the space of all functionals. So your Hilbert space of the complex numbers. And you get the classical Riesz representation theorem, which this is a little bit harder to read here. There we go. Which tells you that the conjugate Hilbert space is the same as the dual Hilbert space. Okay, so these are all things you can do with Hilbert spaces. Great. Now, in terms of operator algebras, whatever your flavor of an operator algebra is, whether you're thinking about C-star algebras or W-star algebras or whatever it is that you like, you should always be able to concretely realize them as acting on a Hilbert space. Right? So this just means that it emits faithful representation. And again, I'm sneaking in what I mean by representation, kind of sweeping that under the rug. But these representations contain interesting data about your operator algebra. For example, its spectrum, you can obtain it as the irreducible representations, or its states, which are cyclic representations together with a choice of cyclic vector, and so on. There's a lot of data about A contained in it, so in rep A. So these objects are worth a study in their own right, but what we claim is that this actually gives rise to a higher Hilbert space. And then if you do it inductively, you'll get higher and higher Hilbert spaces and higher operator algebras. So I'm gonna go ahead and instantiate what I mean by an operator algebra. I'll be using finite dimensional algebras, namely for the reasons I outlined in a couple of slides prior. And we're gonna have these be H-star algebras. So maybe I'll tell you a little bit more about why in a second, but an H-star algebra, especially a finite dimensional one, is a C-star or W-star algebra equipped with a faithful trace. So this just evaluates vectors in A into complex numbers, and then there's a faithfulness and traciality condition that you desire. So one can unfold this data, and what I mean by unfolding will become more apparent later on, but one can unfold this data to say that the data of a finite dimensional A-star algebra is equivalent to a star algebra together with a compatible Hilbert space structure, right? So something that instead of taking one thing at a time, one vector at a time, it takes in two vectors at a time, or a zero sphere. Now, what does it mean to be compatible? Well, I mean this following condition here. Maybe I should zoom in. Right, so this is relating something about multiplication, the star on my algebra, and then the inner product. So one way of saying the same thing is, well, A itself acts on itself, okay. And I can view it as a module over itself. So namely, well, what do I want to say? I guess I don't even need to say this. That's okay. Well, I'll say it like this. Okay. You can take an element of A, and then you can have it act on itself. So I don't know how much do I want to say here? Say act on itself on the left. Okay. Right. So this is sending your algebra to operators on your algebra. Now, if A is a Hilbert space, then this is a Hilbert space representation. So let's see. I'll just save this for now. Maybe make it look better. Right, so this is a Hilbert space. So what this first condition is telling you, this one right here, is that this map is a star preserving map. And then the other one tells you about the right action, which is given by multiplication on the right. Okay, so this is not too surprising. You could abstract this generally if you want, like even more generally if you wanted to, in terms of the Yoneda embedding. I'll do that. I'll do that for a category instead of an algebra, but this is very related to the Yoneda embedding and it preserving the star. So I'll just say that. Okay. Is there anything else I wanted to say here? Oh, okay. Well, this unfolding trick is pretty easy. If you give me, let's say, if you give me a operator algebra with a trace, I can obtain an operator algebra with an inner product. This is by the GNS construction. Okay. And then vice versa, if you give me an operator algebra with an inner product, I can form a state which is associated to the vector 1. Okay, I don't know how useful this is, but okay. I guess you're wondering. So one of them is GNS, and then the other one is choosing the vector 1 or omega. Okay, I'm not really saying much. Great. I don't know if anyone has any questions, but please feel free to stop me at any time. I'm just doing like the very basics, okay? Cool. So talk a bit about representation categories. So if A is a finite dimensional H-star algebra, this is again complete with respect to Cauchy limits, but this is a category now, so I'm not talking about Cauchy sequences. I'm talking about absolute colimits. So given two representations, I can take the orthogonal direct sum, and there's also a correspondence between submodules and orthogonal projections. So this is saying something about orthogonal projection splitting, more generally idempotent split. Okay, and it turns out that these two generate the absolute colimits, so it's complete in this regard. There's also bases, so every representation I can decompose it as a finite direct sum instead of a normal sum of distinct simple representations up to some multiplicity. So here I'm thinking of taking an object in my category and decomposing it in terms of a orthonormal basis. Now, of course, this expression doesn't make any sense, but when I do try to make sense of it, I see that I can write my my representation as a direct sum of simple ones, and here they're scaled instead of by scalars, they're scaled by Hilbert spaces, and this has to do with the Hom space in my category, and I've had to tweak it slightly with some numbers. So all of these projects are kind of annoying, mostly because you have to keep track of all these numbers and make sure that everything is scaled appropriately. So this number here might be weird. Perhaps another way I can write this that might be more convincing to you is I'm going to take this Hilbert space, but this Hilbert space is also a module for end of EI. So these EIs are simple representations. These live in rep A. And EI is going to be an H-star algebra And then EI is also a module over end EI. So I'm going to tensor over this algebra. So this is really what this expression is, and I'm just. It turns out that you can tweak it so that you just have to sprinkle in some numbers to make this decomposition work. But I'm not really telling you the details. But once you think of this as being an orthonormal basis for rep A. Okay. What else? There's also an evaluation. So if you give me an object in rep A, so a representation of A, by that I just mean a Hilbert space. Maybe I should have said this before. It's just some Hilbert space. What is this? So this is just a Hilbert space together with a map from A into B of H. It turns out that you can equip the right A intertwiners with a trace. So I know that that Quan described this in his talk, but just to kind of be more verbose, you start out by picking a vector in your Hilbert space that you're acting on. Now you can construct a ket operator, which goes from A into H. I'm calling that ket psi, adorned with A, just to tell you what the algebra is. And this is just given by acting on your vector with A. Okay, so this is a map from A to H that is just determined by picking out the vector C. So these you can always build, and because both A and H are Hilbert spaces, you can construct the corresponding bra operator, which is just this adjoint. That goes backwards, that goes from H to A. Now, if you pick two vectors, you can define their A-valued inner product by just composing the ket of one with the bra of the other. That yields something in end of AA, but you can easily check that that's just the same thing as A. Okay. And then you can determine a trace on H, on your module H, on endomorphisms of your module by the following identity. Okay. So just as you can define a bracket, right, or a A-valued inner product, which takes values in A, you can also define the ket bra. Cool. So what we're really doing here is, maybe this is kind of a fancier way of saying this. There's a map. Well, first of all, A lives as a module over itself in rep A. And because everything is nice and finite dimensional, all the representations are finitely generated projective. So what this means is that AA, like A as an A module, generates all the representations. So what we're really doing is we're giving A as an A module its own trace, and then we're inducing a trace on all of rep A. So note that, yeah, I guess the trace that we've given this, when we look at H equals A, is the same trace. Trace A is trace A, or the trace that you started out with. Okay. So you could do an alternative description of, instead of defining the trace on a ket bra, you can try to define it on just a general operator. And the way that this works is, well, I view my representation A as coming from as a sub-representation of a large enough free module. And then I use the trace on A to induce a trace on this bigger one. This one's pretty easy. Direct sum of A's. It's pretty easy to define what the trace on that is. and then you can induce a trace on H by including it in and then projecting back out. And this will give you the same trace, okay? But why am I calling this an evaluation? Well, this is a trace instead of an inner product. And what I want you to notice is that a trace is an evaluation of one spheres instead of 0 spheres. It's one spheres. In particular, you see, kind of running out of space. But I can. Oh, okay. The point is, I can feed circles into this trace. Whatever I mean by this. Cool. Great. Okay. So instead of evaluating 0 spheres, I'm evaluating 1 spheres. This turns out to not matter on the orientation. This is telling you something about evaluating 1 spheres on a oriented 2 sphere. But okay. It turns out that rep A is a 2 Hilbert space in the sense of Baez, right? So Baez defined these 2 Hilbert spaces. This was in 97, I said, I think. And moreover, all 2 Hilbert spaces arise in this way. So you can describe what a 2 Hilbert space is abstractly. I'll do that in the next slide. And it turns out that by picking a generator and looking at representations of that generator, it turns out that every 2 Hilbert space looks like this, okay? Cool. So a 2 Hilbert space is particular.
Sorry, Giovanni.
Oh yeah, what's up?
Yeah, I'm wondering if you like how much you can get away with by not doing some sheaf theory, because I can think of, for instance, the like a space that is locally ringed. It's not really a ring. I want to think about like a von Neumann algebra or something, commutative von Neumann algebra. I can think of a space that is ringed in that algebra, and then I can think of modules of that ring that would define for me a sheaf on that space. So that would presumably live in this rep A, right? Or rep, or it would define for me.
Sure. Yeah, I see.
Like it would define for me something in a 2 Hilbert space of some sort. But I'm worried about this Cauchy completeness condition.
Right. So I'm being kind of sneaky here, right? When I'm saying representations, like everything is happening in finite dimensions, right? So these are
okay.
Yeah, these are finite dimensional ones. That's a really good point, though. If you want to do the infinite dimensional version of this theory, you end up having to do sheafy things. Like that is like the correct notion.
Okay.
Yeah.
So because I read this paper by Dave and Andre about this by commutant categories, but they don't mention sheaves, do they?
They don't, and that makes me kind of mad. But
okay.
that is a good point. So Andre has a list of like 75 open problems about bicommutant categories. So you can find this on his website. You can just look him up. It's like one of the first things that shows up. And there's a couple of conjectures there about how these bicommutant categories relate to sheaves. Well, actually, I'm trying to think what he says. I think he talks more about bundles. So this is kind of like the finitely generated projective sort of story. But I do agree that like if you want something more general, you have to do sheaves. That's true.
Because I do know that like the sheaves can't be too nice if you want like some tools that you still want to have in the finite dimensional case. You don't want like coherent sheaves, for instance. Like coherent sheaves are very nice, but it's too nice.
Right. So, it's too nice. Yeah. So that's one of the difficulties about trying to do this in the infinite dimensional story, which is
I've
like
been thinking about this as well, so.
Okay, great. Yeah. Yeah. If you want all modules, like modules for operator algebras can be quite nasty, right? So yeah.
That's true. Yep. All right. Thank you.
No, yeah, for sure. All right. where was I? Okay, so for two Hilbert spaces, again, yeah, everything is finite dimensional and very nice, and everything just works really splendidly. And then when you try to move on to infinite dimensional things, there's all sorts of directions that you can take and all sorts of levels of niceness that you might want to do. But here, a finite dimensional two Hilbert space, I just mean a finitely semi-simple dagger category equipped with a trace. And this is a trace on every object. So it's a collection of traces for every object in my category. Right? So each trace H takes values in end of H. This is a H-star algebra. Spits out numbers. Great. Yes. Okay. And then it has some has a positivity condition, and it has a triviality condition, and a definiteness condition too. Okay. You can unfold this data, so maybe it'll make more sense here. So the data of a two Hilbert space, this is equivalent to a finitely semi-simple dagger category, together with a compatible Hilbert space structure on each HOM. So if I pick two objects, right, I've got my HOM category. I can denote it like this, or maybe more suggestively like this, like an inner product of the object H and the object K, and maybe I'll label it with script H for my two Hilbert space H. And by compatible here, I can just say this in terms of the Yoneda embeddings. So, okay, this might be kind of mysterious. What I mean here is that if I look at precomposition and I fix some objects, precomposition will give me a map from a Hilbert space to a Hilbert space, right? That's because I've equipped all my HOM spaces with Hilbert space structures. And then I want the adjoint of precomposing by some morphism F to be precomposing by its star. And the same thing with postcomposing. So that's one way of thinking about it. The other way of thinking about it is if I just pick an orientation, let's see, which one do I want to do? I'll do the contravariant one. So here's my contravariant Yoneda embedding into this is functors from H to Hilb. Yoneda embedding will do that for me. If you give me two objects, I get a Hilbert space. This is just saying that this Yoneda embedding is star preserving. Okay. And later on, we'll see that this is actually an equivalence, and I can replace H op with H bar by using the star itself, right? So star gives me a map from H op to H bar, and it's an equivalence. So I can think about it like this instead, and then you could also think of this as being the dual of my two Hilbert space H. So this is some sort of Rees representation thing, but I'll say that I think I have to move the slide. Yes, okay. So unfortunately, it gets rid of that, but I'll reiterate that. So here's a table of analogies, right, between functional analysis and representation theory. And so Hilbert spaces correspond to these two Hilbert spaces, which look like representations of H-star algebras. My vectors correspond to objects. Scalars correspond to Hilbert spaces. And as we saw, I think in the previous slide, as you can scale a Hilbert space with a complex number, you can also scale an object with a Hilbert space. So this is this thing right here. You're using when you're thinking about it as concretely, like a two Hilbert space concretely as rep A, then this is just taking a Hilbert space and tensoring it with another with a representation. So I've used H for both of these. Maybe let me use K here. This is for a Hilbert space. This is for something in rep A. I can tensor them by just I just act on the left tensor end. So it's kind of easy. If you want to think about it, maybe even more concretely, if my Hilbert space is C to the N, I tensor some object, some abstract object. What's a good letter for an object? X. And this looks like X to the N. You have to do it coherently. This is a functor, so okay, whatever. What else? You've got addition. Addition corresponds to orthogonal direct sum. For Hilbert spaces, you have a complex valued inner product. Here you have a Hilbert space valued inner product. And then corresponding to the dual Hilbert space, you have the pre-sheaf category of all functors from H into Hilb. Maybe here I should note that like this is happening for finite dimensions, right? So like for finite dimensions, like even say, for example, for a Hilbert space, I can just look at all functionals. But if you're doing things in infinite dimensions, you might want bounded functionals. So the corresponding thing on the other side, you wouldn't want to look at all pre-sheaves, but you would want to look at continuous pre-sheaves. That sounds more like a sheaf to me, right? So you kind of have to be more careful when you're doing this. Anyways, or you can, yeah, okay, I won't say more about that. And then corresponding to the Riesz representation theorem, which tells you that the conjugate is isomorphic to the dual, you get, this is the Yoneda embedding theorem together with semi-simplicity. You can show that the conjugate to Hilbert space is equivalent to the dual Hilbert space. Again, this is like by the Yoneda embedding that I was mentioning earlier here. Okay. So that's two Hilbert spaces. I should probably move faster. Okay. So luckily, because everything is in finite dimensions, you can talk about operators without having to worry about boundedness. So by operator, I just mean a functor, a dagger functor. So just it's preserving the star and I guess the linear structure. One example is that if you give me two H-star algebras A and B, and then you give me a bimodule, this gives rise to a map from rep A to rep B, just given by tensoring over A with the bimodule M. So that will take some representation of A and give you a representation of B. This turns out to be a dagger functor from rep A to rep B, and we show that actually all operators arise in this way. So this is kind of not too hard to show, okay? What else do we do? Let's see. So if you have operators between two Hilbert spaces, you might want a adjoint operator or a unitary adjoint operator. And so we determine this, I should zoom in a little bit more. For an operator from H to K, you get an F star. Here I'm using a 5-pointed star for some reason, but okay. That goes backwards, and it's determined by the following relation. So one way you can think about this is as them being as F star being the adjoint as a functor, but these two spaces, right? As we said before, they're Hilbert spaces, so we want this equivalence to be a unitary. So I'm denoting that with a dagger. But I've also used this notation suggestively so that you think about it as an inner product. Okay. And so this is very similar to the relation one level down between an operator and its adjoint. Luckily, everything will be both a left and a right adjoint, and you can show some similar properties. So the dual of the composite is the composite of the duals, but it gets flipped because everything's contravariant. And then if I take the adjoint of the adjoint, that's just the same functor or operator. Now back to that example that we were looking at for bimodules, right? So for a bimodule of H-star algebras, the dual bimodule you can think of as having, well, its underlying Hilbert space is the dual Hilbert space, and then the action is given by precomposing that swaps the left and the right actions. Or equivalently, if you prefer to think about the contragradient bimodule, you can just look at M bar. So it's the vectors look the same, but then all the actions from the complex numbers and A are twisted by a star. And then, these are the same by the Riesz representation theorem. So pick whichever model you want. Anyways, the adjoint of the operation, the operator given by tensoring with a bimodule turns out to be tensoring by the adjoint bimodule, or the contragradient bimodule. Here, I guess I use both. Okay. Anyways, great. So this is saying something about some functor in the background being star preserving. But okay, cool. We also have operators between operators, of course, because these are categories. So between operators onto Hilbert spaces, you have natural transformations between them. If you want to do the infinite dimensional story, you can't just look at all natural transformations. You might want them to be bounded, or maybe have some more properties so that they're well behaved. But again, finite dimensions, I'm just going to look at all natural transformations. And back to the previous example, if you give me a bimodule intertwiner, that induces a natural transformation between the functor associated to the source bimodule and the functor associated to the target bimodule. Okay, this turns out to be a natural transformation, and all natural transformations arise in this way as well. Okay, cool. Great. So as we saw, we had an adjunction for functors, but there's actually a second star or a higher star. So here I'm using a 6-pointed star instead of a 5-pointed star. I don't know. I was trying to be cute when it came to naming my stars, but this one has 6 points. Great. So it takes a natural transformation, and on each component, it just applies the adjoint. So this adjoint is happening in the target to Hilbert space, but you should think of this as a vertical flip, right? So if eta went from a functor f to a functor g, then eta star will go backwards. So here I have some sort of oriented disk, and I flip the orientation. You'll notice that I'm doing something kind of weird here, where I'm choosing not to use string diagrams and use pasting diagrams instead. That might be a weird choice, but that's just what I chose to do. Okay. Great. So back to the bimodule example. If you give me a bimodule intertwiner, that's a map between the underlying Hilbert spaces, and I can take its adjoint. You can check that that's also an AB bimodule intertwiner, and so this adjoint, right, the vertical adjoint, this 6-pointed star of the associated natural transformation to F, is given by well, the same thing, but with the adjoint map. Whereas the horizontal one, I guess it depends on whether you're thinking about it as being the dual bimodule or the contragradient bimodule, but this one's just given by the conjugate bimodule intertwiner. Okay. Great. So we're looking at two Hilbert spaces, two Hilbert spaces, and then functors and natural transformations, and we're seeing that there's not just one star but two, and in particular this star, this vertical star, helps equip the category of functors from a 2 Hilbert space to another 2 Hilbert space with a 2 Hilbert space structure. So namely, there's a trace. So the trace valued on a particular object, f, right? So f is some functor from h to k. It eats endomorphisms. So here I have this endomorphism eta, which I'm viewing as a disk from f to itself. And this is given some horrible formula. So this is some sort of like co-ND thing. And I guess you could also think about it as state sums, but if you wanted to use more continuous language, you should kind of think about this as like integrating your natural transformation over the source H. So you'll notice that you have some coefficients here related to eta at a particular basis vector. And then here you have essentially the dimension of that that basis element, and then you're summing over them. So this is kind of like an integral. Okay. More stuff. Oh man, I have so much stuff. Okay. So if you look at the prototypical operator 2 algebra, that is the operators from a 2 Hilbert space to itself, together with its natural transformations. This is a 2 Hilbert space, by what we just said. But it also has a tensor product, right, given by composition. So it's got a tensor product, it's a 2 Hilbert space, and it's got 2 involutions. It's got a vertical one and a horizontal one. Okay. So this is kind of an artifact of the fact that I haven't used Poincare duality to flip my pacing diagrams into string diagrams, but right, for a given operator, I have an evaluation and a co-evaluation map with it and its dual. I'm choosing to represent them as disks. Right, so this is let's see, this is a disk from F dual composed with F to the identity, and I'm choosing to contract this identity down to a point. So some sort of like oriented disk that just like contracts the disk down to a point like this. And you've got a similar co-evaluation from the identity to F composed with its dual. I'm choosing to contract this to a point. Great. And so this is like, yeah. Okay. Cool. So I'm going to use these disks to build some spheres. That's essentially what I'm going to do. So this is kind of a folding trick, and then I'll unfold later. But if I restrict the trace on B of H to the identity, well, what I notice is that endomorphisms of the identity, these are natural transformations from the identity to itself. It's like if I contract both loops, this looks like spheres. So you can think of this as pi 2 on this 2 Hilbert space. Right. This is a commutative operator algebra by the Ekman-Helton argument. And moreover, when I look at the trace restricted to this space, it turns out to be a spherical weight. So what I mean by a spherical weight is that I can build spheres. There's like a front-facing sphere and a back-facing sphere. They're oriented, so that's how you tell which one's which. And then for any endomorphism of a functor, you know, taking it and then looping the sphere around the back is the same thing as looping it around the front. So the spherical weight is an evaluation of oriented 2 spheres. You can think of it as oriented 2 spheres and a 3 sphere by this property. And it turns out that from this you can recover the trace, and then you can recover inner products. So this is the kind of the principle of folding here. It's already 10:25. How much time do I have? Like, when should I be ending the talk?
In fact, it's okay. You can take, if you need 15 minutes, you can take 15 minutes. It's okay.
Wait, how many?
How long do you do it?
I've got, how many slides do I have? Say maybe 10 minutes.
Okay, it's okay. It's okay.
Yep. All right. I'll try to keep moving along faster. Okay. Cool. So this is your example of a prototypical operator 2 algebra, right? All operators on a 2 Hilbert space. But this kind of informs you about what the definition of an operator 2 algebra should be. So by an operator 2 algebra will mean, again, everything is finite dimensional, an H-star multifusion category. So this is some multifusion category. This is like the higher version of a semi-simple algebra. You've got 2 involutions, and then you've got some spherical weight. And the spherical weight will give you traces and will give you inner products by unfolding. So In particular, you can view this data as being equivalent to a unitary multifusion category. So this guy only has one star, the top one, together with a unitary dual functor. That's your second star or your second involution. And instead of having a spherical weight, you ask for a compatible two Hilbert space structure. So, right. So this is asking for traces instead of spherical weights. How do you ask it to be compatible? Well, it's the same condition as one level down. You've just like upgraded everything a category level. Okay, so this will seem very familiar to the axiom that you asked for in H-star algebra. And this is telling you something about how, how it should be a dual functor, but in a nice unitary way. Okay. And again, this is telling you something about the Yoneda embedding, and this is kind of secretly telling you that Yoneda should preserve this 5-pointed star or unitary dual functor. Okay. So back to a table of analogies, right? You've got algebras, and then you've got tensor categories. So finite dimensional algebras will correspond to multifusion categories. Star algebras will correspond to these unitary multifusion categories. That's one star, together with the UDF or unitary dual functor. That's a second star. Equivalently, you can think about this as just being a bi-involutive tensor category, and you need some conditions to go back and forth, but okay. And then the trace corresponds to the spherical weight. H-star algebra corresponds to H-star multifusion category. And in particular, operators on a Hilbert space correspond to bimodules over an operator algebra. Right, so this is viewing my operator algebra as representing my two Hilbert space rep A. Okay, faster. Again, you can study representations of an H-star multifusion category now. So you just write down the naive definition. It's just a representation as a unitary multifusion category. Okay. This will again be complete. You have to be kind of careful about what you mean by complete, or like what are the right direct sums versus projections. So here, what you'll want is these things that we call Hilbert direct sums. They're kind of like the difference between like orthogonal direct sums and direct sums, whatever that is, but one level up. So essentially, you want things to play well with. It depends how you think about it, but either with the stars, with both stars, so that everything is unitary in its corresponding level, or that it plays well with the spherical weights. Okay. But anyways, there's so-called Hilbert direct sums. For representations, this is quite easy. You just take the two representations and you and you just write them next to each other. It's like pretty easy. Maybe something I should say here is that these representations are tensor functors from A into end of H, or I guess I called it B of H. So B of H is for a two Hilbert space. Okay. So this is kind of looking like quantum symmetries here. Tensor functor. Well, it's tensor functor and it preserves everything, like although it preserves the both involutions. Okay. There's also a correspondence between submodules and like higher projections. It turns out that here we call these H-star algebras, but they're H-star algebras internal to this monadal category. So I know that Quan talked about these and kind of went into more detail about them. I'm kind of gonna ignore this and just say that these are like the higher analogs of orthogonal projections. These are the analogs of orthogonal direct sums. Okay. Now you also have bases. So this is part of what we're working on more recently. So maybe I should have said that before. I guess I'll say it at the end. So we've got this manuscript that we're writing where we're checking more details that were left to do in the 3-Hilbert paper, this 3-Hilbert space paper. So one of them is this corresponding to these bases. It turns out that you can decompose every module category in terms of a basis, whatever that means. You've got a similar formula. And it turns out that you can do this coherently and that it's actually not evil, or that the space of all these bases is, again, contractible. Okay. What else? You've also got this evaluation. Now this is an evaluation of 2 spheres. They're oriented. They live on a 3-sphere. Okay. You've got a similar formula. It looks like an integral. It's some sort of whatchamacallit? No, state something. Okay. But just as before, right? When I look at representations of an operator to algebra, this should give me a higher Hilbert space, or a 3-Hilbert space. So we show that this is a 3-Hilbert space in our sense. I'll tell you what it is in a second. And moreover, every 3-Hilbert space arises in this way. So formal definition, 3-Hilbert space is a finitely semi-simple dagger 2 category. That's 1 star. It's equipped with a unitary adjoint functor. That's a 2nd star. And then you've got the spherical weight, which again, because of unfolding, you can always trade that in for traces or compatible to Hilbert space structures on each hump category. You could trade those in further for inner products. So everything is dualizable enough that you can fold things in and out, so that at any point you only really need evaluations of n spheres, and then you can turn that into evaluation of n-1 spheres, blah, 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 all the way up to 0 spheres or inner products. Right. So the data of a 3-Hilbert space, again, it's equivalent to a finitely semi-simple dagger 2 category with a 2nd star. And then compatible to Hilbert space structures. So it's like enriched into Hilbert spaces. That's something else that we show in new work. Such that the Yoneda embedding is not only preserves the star, like the dagger or the 6-pointed star, but it also preserves the 5-pointed star. So right. So in current work, we've done a couple of things. So one thing that we've checked is that there's a tensoring. So for every 3-Hilbert space, you can scale an object in H by a 2-Hilbert space to yield another object, and you can do this coherently. So this is this tensoring. It's also self-enriched, right? So this is kind of this claim right here. Looking at Helm functors does give you a 2-Hilbert space structure. This is your 2-Hilbert space valued inner product. And then moreover, this is theorem. We've shown that the Yoneda embedding is actually an equivalence. So you actually get like this Rees representation theorem sort of statement. Okay, so this is all work that I guess it's been kind of recent. I guess we finished these 3 proofs about a month or 2 ago, and now we're just kind of writing everything up and cleaning everything up. Cool. So let me get to the punchline. Okay. Okay. So we saw that rep of any H-star algebra, H-star multifusion category is a 3-Hilbert space. In particular, if I take the dumbest one, the category of Hilbert spaces with its tensor product, that's a H-star multifusion category. That's just 2 Hilbert spaces. This is kind of the same thing as like rep of the complex numbers is category of Hilbert spaces. So that itself is a 3 Hilbert space. Moreover, there is a Morita 2 category of H-star algebras, bimodules, and their intertwiners. This forms a 3 Hilbert space, and then what I've been describing in the talk all along is that there's actually an isometric equivalence of 3 Hilbert spaces. So this is something that we showed in the 3 Hilbert paper. So this just sends an H-star algebra to its category of representations. Here, if I have 2 of them, send them like this. If I've got a AB bimodule, then that corresponds to tensoring with that bimodule. And then if I've got a natural transformation, I'm not going to write it down, you get the corresponding if you have a bimodule intertwiner, that gives you a natural transformation. And so all these statements that we've been accumulating just tells you that this is an equivalence, but not just of 2 categories, but actually of 3 Hilbert spaces. So it preserves, this preserves the top star, the bottom star, and the spherical weights, which is pretty nice. So they're the same 3 Hilbert space. In the paper, we also showed something more general, right? So this was for the particular case when my H-star multifusion category was the dumbest one, so the category of Hilbert spaces. More generally, right, we have that the representations of any H-star multifusion category is a 3 Hilbert space. You can form a similar construction to the Morita category of H-star algebras, but you can do it internal to any H-star multifusion category. This is a kind of a formal process. And then you can again show that these 2 are equivalent. Right? So representations of your H-star multifusion category are the same thing as H-star algebras internal to this H-star multifusion category. And moreover, you can kind of soup this up even further and obtain an isometric equivalence of C-star 3 categories. So these were things that I defined in the paper I called F, an operator on C-star 3 categories. And so essentially this lifts to a construction where you take any H-star multifusion category and you produce rep A. This is the same as H-star alg A. This turns out to be an equivalence of C-star 3 categories. So that's something that we show in the 3 Hilbert space paper. But what we show more recently in this preprint in this manuscript that we're writing out, that it's actually isometric. It preserves a whole bunch of stars. There's the problem is these are really supposed to be 4 Hilbert spaces, which is kind of tedious, but there's 3 stars. There's like a top one, a middle one, and a bottom one. So 6, 5, 4 points. Okay, doesn't really matter. So kind of spend our time defining what all these adjunctions are at all these levels in these 3 categories and checking that that everything works out. So back to the program. This is where I'll end. We saw that there's this whole chain of Hilbert spaces, 2 Hilbert spaces, 3 Hilbert spaces, and so on. What we showed in our paper was that, well, there's a formal construction by which you take one of these and produce H-star algebras inside of it. And this is really kind of independent of the level. So for 2 Hilbert spaces, you can define H-star algebras inside of that. That gives you H-star multifusion categories. So there's this formal construction, which we call descent. Great. And then, you can take representations, and representations of an H-star algebra gives you a 2 Hilbert space. Representations of an H-star multifusion category give you a 3 Hilbert space. I guess we don't really worry too much about this level yet, but we show that this functor of taking representations, this is an equivalence, and it's an equivalence in the suitable sense. Yeah, is there anything else I want to say here? Yeah, and I guess in recent work, we've been mostly worrying about writing down bases for 2 Hilbert spaces and 3 Hilbert spaces, showing that these are coherent, and using them to show things about adjoints of operators between 2 Hilbert spaces, and in particular 3 Hilbert spaces. So I think I'll end there. Sorry for going a little bit over, but yeah, I'll stop here, and I'll stick around for questions.
Thank you very much. We start. Can you hear me properly?
Yeah, I can hear you. Yeah.
Yeah. So my first question is, so you show a dictionary between, I guess it was the slide 14, dictionary between a star algebra and multifusion category.
Oh, this one? Yeah.
Yeah. What is analog of a factor? A factor.
Ah, right. Yeah, so that's a good question.
I guess it's not replacing multifusion by fusion. I guess it's not that.
Yes. So, right. So you can still write down what the center of a tensor category is. So this is for a little category. So one level down, right? You just ask this to be trivial. So to be the complex numbers. Here you could ask this to be Hilb. That's fine, but somehow this might not be good enough. It's kind of a pain in the butt, but really, somehow these aren't algebraically closed in a suitable sense. So you might want this to be super Hilbert spaces. So yeah, but you could ask just for this. Now, when you're talking about factors, you're also really talking about like W star things, right? And you probably also want them to be infinite. So if you want like a suitable analog for a W star algebra here. I think somebody mentioned this before, that they were reading this paper on Bicommutant categories, but those seem to be pretty good analogs for W star algebras. Here there are Bicommutant categories. So at the moment, there's only like a very extrinsic definition of these things. So this is kind of like the most straightforward thing that you could write down. It's let's see how much adjectives do I want to say. It's a tensor category instead of an algebra. You might want some stars, so maybe it's a unitary. I'll just say it's a W star tensor category together with a map into BIM-A. This is for a W star algebra. And so this is like making them very concrete, right? So like an operator, a W star algebra I can view as living inside a B of H. I'll do it more. It's more concrete. And once you have it inside of there, you can talk about the commutant. I don't know if you want to see the definition of that, but essentially you can talk about the commutant, and then you can take the bicommutant, and then a bicommutant category is just one, which is there's a particular map here, but I'll just say this. It's organically equivalent to its bicommutant. And so you can talk about commutants and bicommutants and centers. These are all like very well-behaved constructions, even as you move up in category level. And so yeah, you could look at one of these and ask for its center to be trivial or to be almost trivial. Does that answer your question? I don't know if you wanted more detail or less detail.
And so on the other side, if you focus on fusion category instead of multi-fusion, what do you have in the best? Do you have only trivial algebra?
So right. Guess if you're thinking about factors, I guess you'll definitely want them to be fusion. Right, because I mean, yeah, multifusion is telling you about how to decompose the unit. So yeah, I guess like the difference between fusion versus like multifusion is whether I can like decompose it into these indecomposable blocks or not, or if it's just like one solid block. Yeah, at least for this story, like multifusion is completely fine, right? Like the picture that I have of a finite dimensional. Ooh, well, I said algebra, but really I mean like a finitely semi-simple algebra. This is a multi-matrix algebra, so it just looks like a bunch of blocks. This is what every finitely semi-simple algebra looks like, and then what is the number of blocks? Well, it's the same as the central projections. Minimal, I guess, minimal central projections. So essentially, I look at one and I view how I decompose it, and there's one minimal central projection for every block. And so this is just telling me something about how to decompose one as a sum of projections. And so analogously in the multifusion case, like if I look at my unit object one, well, how I can decompose it into simples, this is telling me something about the blocks, but I kind of don't want to get rid of them for this story, if that makes any sense. Yeah, if you're coming at it from factors, then you definitely don't want these like minimal central projections, right? Does that answer your question?
Yeah, yes.
Okay. So, yeah. Are there any more questions? I don't know if I gave you the detail that you wanted. It's kind of hard figuring it out from Chuen's talk, but hopefully this helps clear up some details that maybe weren't clear, and maybe gave you some nonsense that he might have not been able to say.
So let me ask another question.
Sure.
So if you go to your last slide with you're going to. So do you expect a global understanding for n higher Hilbert space for general n, or do you think it will be? In fact, I asked the same question to Quan Chen when he gave a talk several weeks ago.
Oh yeah.
Do you expect the existence of a global understanding for in general? And
I really hope so.
What are you doing?
At least in finite dimensions. I think that. So there's a project that we have right now. So this is with my advisor. And then Lucas Mueller, and Luke Stehauer, where where we're trying to describe this picture in terms of homotopy fixed points. So this is kind of like in the same flavor as this like paper with a lot of people on dagger n categories, and it's trying to write things down in terms of fixed points of groups, but you're doing everything weakly in an infinity n category. So at least for this project, we're kind of more focused on describing the different flavors of operator algebras. So like C star algebras, W star algebras, H star algebras as homotopy fixed points of different groups. They're all subgroups of ON. I mean of O2. And then when you look at the representation categories, it kind of carries along. So we expect that you should be able to. It gets a little bit trickier when you do n. We had this problem. We were running into this problem here when we were doing these dagger n categories, where at a certain point, instead of ON, you have to look at PL for some like weird reason. But I do expect that eventually people will be able to figure out how to write these in terms of homotopy fixed points, especially for Hilbert spaces, because they're kind of supposed to, finite dimensional and Hilbert spaces. They're kind of supposed to be easy. And I think it'll come back to this like evaluation of n spheres and like right, like being a homotopy fixed point of these groups, you can write it down concretely as like trivializing some actions, and when you start looking at what those are, you start getting these like these higher daggers and how they're supposed to interact. So that's like this story here with the dagger n categories. Now you when you want Hilbert spaces, there's some problem with like positivity, right? So like an inner product, for example, you want it to be positive. Like if you take two things, you want them to be positive. And somehow that's a little bit trickier. But for example, Stehauer has a paper on like Hermitian objects and how to turn them positive. And it seems that all of that is along the lines of homotopy fixed points, even though he doesn't quite write it like that in that paper. I think there's a current manuscript that they have where they describe everything from that story in terms of homotopy fixed points. So you might be able to get away, describing this like positivity condition also in terms of like fixed points. So I don't know how helpful that is, but I do hope that people will be able to do it and give a fully fledged definition for general n.
More question? Okay, so there is no more question. Let's thank you again.
Yeah, well, thank you so much for having me.
Thank you. Nice talk. And bye-bye. Bye-bye.
Yeah, all right. Have a good day, everyone.
Good night for you.
Yeah.